Hello all, I just wanted to show you and explain some things about the signal that is fed into the knock pin on the ECU and how it's done basically. It's a sweep that runs from 100 Hz to 35K, and the window is around 10, it's exactly 10 milliseconds after each ignition event. So the signal is not present if there is no ignition event. So it's not a random sweep, it's a synchronized sweep after. So the ECU can detect it. This was done because I wanted to see if there is a certain amount of windowing going on after a ignition event, or if the ECU is sampling the knock data at regular intervals instead of dynamic, so to speak. So this is the signal and how it sounds if I play it back in Audacity. It's exactly like you saw it in the video, and I will explain a few things so that everyone that's not up to par with how acoustics works in electronics, cables, speakers, and so on. There is a certain amount of energy in each audio frequency spectrum, so to speak. In the lower octaves you have high intensity, and in the higher in the higher octaves you have low intensity. That's why the waveform looks almost like a hit on the drums, so to speak. It's high intensity at the lower and low intensity at the high, and I will show you how this works. We can zoom in and look at the individual pulses that are sent to the ECU. So when we send this pulse, it's 6 milliseconds long. This is sent right after the ignition event took place. So this is not a random send, it's a actual send to trigger the ECU to detect knock. And the total length is 12 milliseconds. This is because we run at 4100 RPM, so we can detect up to 15 milliseconds per RPM and event. So we have a wasted spark system on our cars, so this event is triggered for, say, number 1 cylinder, and this is triggered for number 4. So it's not sampled at half the crankshaft RPM, since a Otto cycle is 720 degrees. It's sampled every time for number 1, number 4, number 1 again, number 4 again, and so on and so on. You can see that the intensity is a medium here, but in the beginning of the file, where we run at a lower frequency, you can see the intensity is almost up to clipping, and here you can see the actual pulse length. It's very, very, very short, so it's not a actual exaggeration to trigger knock. It's actually the lowest possible duty cycle you can set for the Arduino, so it's not a provocative signal at all. And you can see as it gets up in the frequency band, you can see the distance between each signal is getting smaller and bigger and smaller and bigger. This is called interference, and this is why we see the reflection back from 15K down to 7500K and below, and it still triggers a knock event even though we are past the main knock window. And you can see these lines. These lines are getting pretty tight now. This is because this is one frequency, this is another, third, fourth, fifth, and sixth, and so on. And I will show you how this works soon. And you can see up here we have a lot of static, or what you want to call it. So if we zoom out and change to spectrum, you can see what I mean by high intensity in the lower frequency bands. So if we say 2K, we are here, we have a reflection at 4, we have a reflection at 6, 8, and so on. If we choose another band, we say at 4K. 4K we have a reflection at 6, 8, 10, 12, and so on and so on. This is the main carrier wave, if you will. These are reflections back in the cable, so to speak. And I will show you exactly why we get reflections back from 15K down to 7K. And this is because at 15K, if we go, let's zoom it like this, easier to see. Now we are at let's see. This is the carrier wave at 15K. And you can see what's happening over here. It's turning back down in frequency, even though we have a frequency that's going up all the way to 35K. This is because our sample rate is 44 K. Therefore we can only sample at accurately up to 22K. If we were to sample all the way to 35,000, we would have to double that sampling rate to 70K. This is the Nyquist theorem, and here you can see how it works in reality. Some say, hey, it's bullshit, you don't have to sample audio at higher frequencies than 44K. Yeah, well, it's not bullshit. You can do this on your own equipment, and if you don't believe me, you can have harmonics. You can try this at home. You can provoke harmonics way up in the audio spectrum that causes reflections back to your audible spectrum. Here it's at 13K, 14K, and you will most definitely hear it if you get interference back. This is a standing wave in cables, in connectors, in all your leads in your audio equipment. So some say, yeah, audiophiles can't hear this equipment is better than that equipment. Yes, they can actually hear it if you know what you're looking for. And here you can see it for yourself in black and white. All these are reflections back into the audio spectrum. This one doesn't end here. It goes down all the way down to the audible spectrum. Even though the intensity is very, very weak, it causes a interference pattern in your ears, and you will hear it as a murky sound. It's so you can see for yourself that high quality, high-end audio equipment is necessary for doing analysis on a serious level, since we are just working with signals up to 15K. We don't need stuff like that. So let's look at the pulse width. The pulse width is from the start to the end is 10 milliseconds on the dot every time, every ignition event. So this is the pause when the engine is not igniting anything, like ECU, and this is like cylinder 1, 4, 1, 4, 1, 4, and so on. And you can see the intensity is pretty high, even though the duty cycle is low. But I will show you how a real knock sounds and looks like. This is a real knock. You can see the events going on here. But if we go to a spectrogram, you can actually see it's white. It's a very high intensity. As you can see, the spikes are almost up to 0 decibels. And decibels are from 0 back to negative numbers, not the other way around on recorded signals. So this signal is not even near to begin being white. We are in this spectrum. This is the noise level of the ECU, and this is what causes phantom knock. This one. I am triggering real knock events with a signal that's equally strong to this drivetrain noise, if you will. I am triggering real knock events with signal that is equally weak. And here we have a real knock sounds. We can take a listen how they sound. Listen for the sharp chirping sound. That sounds like a bug or something. And let's play it back at 1% speed. You can always hear it. Sounds like a sonar on a submarine, but this sound is quite different. Let's put it at 7K as we had on the other sample. This is centered around 6.5, something like that, 7K. And if we run this at 1%, you can hear it. It's nowhere near the intensity of the real knock. It's at minus 24 decibels, and a real knock is at 0 decibels. 0 decibels is the recorded level without gain, and it's a very, very high level. We can do some filtering and see what happens. We can apply a filter that I made, DSM knock sensor window, from 1500 Hertz up to 7.5. And if you apply that, you can see we are cropping out the lower and the higher parts of the frequency spectrum. And now you can hear the knock. Much clearer. This is what the ECU hears, and this crap here is what it also samples. So when it hears the knock, it also multiplies this into the equation up to here. So this is real knock, but if we don't have real knock and this portion here is high enough, we get phantom knock. And that's what happens when you put bigger cams in your car and the valves float and the cylinder is not evacuated properly. You have a transmission that you have been beaten on for years and stuff is not tight anymore. Drive axles that are, you can get the idea what I mean. This is phantom knock induced. This is real knock. So if this level gets to this level, and you can see the white spots indicate that it's very, very easy to trigger a real knock with just this crap around here. Let's filter out this on a pure signal and see what we get. Yeah, this is the same signal as we had in the real knock scenario, and you can see what happens. The multipliers that I'm speaking of are these frequencies. If you say if you got knock at 7, say 6.5, then you also get crap at 3, and it's consistent with the log I showed you previously, that it indicates the main window is from 1400 Hz up to 7.5. If we instead had filtering from 4K up to 8K, we would never have phantom knock ever, and that's the God's honest truth. If you can see it for yourself, from 5K down to 0, there is a ton of crap on a properly running engine, and that's what causes phantom knock. Okay guys, I hope some of you learned something new, and for some of you this is just a repetition of previous skills you had. If you're into audio and cars at the same time, you can have a lot of fun and listen to strange stuff that's going on. You can actually use a piece of pipe or a broomstick or something like that and listen to your power steering pump, the alternator, the injectors clicking, and so on. You can hook up can actually tape a microphone to a broomstick and point it to make physical contact on different parts of your engine and record sound and listen to it and import it into Audacity and do experiments like this. And yeah, please share. Have a good time. Bye.